and the water. Then second, I told there is another modeling construct that is a transition, which is represented by the rectangular box. And there is only one transition in this figure, and the places can be connected with the transitions, and transitions can be connected with the places, and with the help of the directed arc. So if you see in this figure, there are the three directed arcs. One is connecting hydrogen place to transition T. One is connecting oxygen place to transition T, and one is connecting transition T to water place. And there is a weight, there is a numeric number that is assigned on each of the arc, that is known as weight of the arc. For example, in this figure, the weight of the arc which is connecting hydrogen place and transition T is 2. And weight of the arc which is connecting oxygen place and transition T is 1. Because I have not assigned any weight, so by default, it is treated as 1. Or otherwise, you can assign 1 as a numeric number. So, and the weight of the arc that is connecting transition T and water place is 2. Now there is another modeling construct. You can see there are the embedded circles inside the places, and these embedded circles are known as tokens. For example, hydrogen contains the 2 tokens, and I am representing these 2 tokens to represent the 2 atoms of the hydrogen, because hydrogen contains 2 atoms. So what I wanted to emphasize on a point, it depends on the context basically, what actually you are modeling. For example, if I want to model here in the chemical equation, I'm representing these, I'm using these tokens to represent the number of atoms. So hydrogen contains the 2 atoms, similarly oxygen contains 2 atoms. So I have taken the 2 tokens to represent oxygen, right? So when we will be seeing the case study, we will see that these tokens are representing something else. Okay. Now, if you see the distribution of the tokens represent the state of the system. So here, if you see the distribution of the tokens in this figure are 2, 2, 0, because 2 tokens are in hydrogen place, 2 tokens are in oxygen place, and 0 tokens are in water place. And this represents the initial state of the system. So the first state of that system, if you see the chemical equation, it represents the left side of this equation, that is 2H2 plus O. Now I have to convert it into water. It means I need to change the state of the process. And as I said, the state of the process is represented by the distribution of the tokens. So I have to change the distribution of this token. But there is a rule which basically decides how the distribution of the tokens takes place. So when the distribution of the token can only be changed if at least one transition in the Petri net figure is in enabled state. That is very important to understand. So here in this figure, because there is only one transition, to change the distribution, the transition T must be in enabled state. Now, what is the enabling criteria of the transition? So the eligibility criteria of enabling the transition is that all the input places must contain sufficient number of tokens. So the input places, if you see for this transition, are hydrogen and oxygen. And these 2 input places must have sufficient number of tokens. Now, what is the sufficiency criteria of the token? And the sufficiency criteria of the token will be decided by the weight of the respective arc. For example, in this figure, the weight of the arc which is connecting hydrogen place and transition T is 2. So hydrogen place must contain at least 2 number of tokens. And oxygen place must contain at least 1 number of token because the weight of the arc which is connecting oxygen place and transition T is 1. So it should be in AND logic. There is no OR logic. So hydrogen, in this case, hydrogen place and oxygen place, they are containing sufficient number of tokens. It means in this figure, the transition is in enabled state. And when it is in enabled state, it fires. And after firing, the movement of the tokens from the input places to the output places occurs. But how many tokens should be moved out from the input place and how many will be deposited to the output place will be governed by the weight of the respective arcs. For example, in this figure, because the weight of the arc that is connecting hydrogen place and transition T is 2, so after firing of transition T, the 2 tokens will be moved out from hydrogen place. Similarly, 1 token will be moved out from oxygen place. But how many tokens will be deposited to the output place? That also will be depending on the weight of the output arc. And the weight of the output arc is 2. And hence the 2 tokens will be deposited into the output place. So one interesting fact that I can draw here is there is no law of conservation of token. The movement of the token from input places to output places depends on the weight of the input and output arc. So although the 3 tokens has been moved out from this figure from this input places, but only 2 tokens will be depositing to the output place. And so the next state will be like this. So the 2 tokens has been removed from the hydrogen place and 1 token has been removed from the oxygen place and 2 tokens has been deposited to the water place. And this is the next state. It has been converted into the water. And as I said, the state of any system is representing or is represented by the distribution of the tokens. So the distribution of the token now it is 0, 1, 2. Earlier it was 2, 2, 0. Now with this, I would like to introduce a concept of reachability graph. And reachability graph basically it is just a graph of total possible number of states that will occur during the operational life of the system. So for example, in this case, the first state is 220. After firing of T, it has become 012. So now you can see this is a dead state because here the transition T is not in enabled state because the hydrogen is not containing 2 atoms, those 2 tokens, right? So but although the oxygen is containing sufficient number of token, but both input places must contain sufficient number of tokens. So this is a working mechanism. And let us try to now take the case study of a reactor protection system, which is a complex control system and it comprises several safety electronic and mechanical components, which are known as nuclear safety components. And it is basically used to safe shutdown of nuclear reactor. Now let me directly switch to the pictorial representation or the schematic diagram of the case study. So this is a reactor protection system or known as shutdown system. We can also say the shutdown system. And let me first explain this system because our model will be based on this case study, and then we will be modeling this case study using Petri, and then we will perform the safety analysis of that Petri. So in this figure, if you are able to see in the right hand side, there is a spherical shaped structure known as calendria, where calendria is written. And here for fission reactions, the fish chain reaction is taking place. And we all know like the working principle of nuclear reactor, but still I would explain who if somebody don't know. Then in this calendria, what happens? There's a nuclear fuel. Generally, uranium is treated as a nuclear fuel. And because of its heavy nuclei, it undergoes the spontaneous fission. And when it undergoes the spontaneous fission, two or more radioactive components takes place, as well as in one fission reaction, 2 to 3 neutrons takes birth and 220 million electron volt of energy gets released in one reaction. And now these 2 to 3 neutrons, each neutron will be responsible to generate one nuclear reaction. So this neutron strikes to the uranium nucleus and it undergoes the same fission reaction, means construction of two radioactive components and 2 to 3 again neutrons, and then 220 million electron volt of energy. And you can see because in every reaction 2 to 3 neutrons are getting generated, and these 2 to 3 neutrons are again responsible for individual separate fission reaction. So huge amount of neutron population is there, and the huge amount of energy, because in every reaction 220 million electron volt of energy is released. So much of heat energy is basically getting released, and hence there is a control system which basically controls the population of the neutron, so that the entire process will remain in equilibrium, and we should not, the existing mechanical component should be able to accommodate this much of, or should be able to sustain in such a high temperature, fluid. So now, but when control system fails to regulate this neutron density, then safety systems comes into the picture. And this shutdown system is one of the category of the safety system, which basically terminates the neutron or which terminates the fission reaction. And how it terminates? It basically eats up all the neutrons. And how it eats up? Now let us try to understand the process. So ultimately, it injects the poison into this calendria. And that poison has a property that it eats up all the neutrons. So if you are able to see inside the calendria, there is a horizontal pipe containing so many tiny holes. And from these holes, basically, the poison can be injected into this calendria. And if you backtrack this pipe, you can see it is connected to a tank where the poison tank is written. And in this poison tank, this poison is filled basically. And you can see on the top of this poison tank, there is a floating ball, and this floating ball is for the smooth injection of this poison. So basically, whenever there is a demand to shut down our nuclear reactor, there is a pressure gets generated, or the floating ball will be pressurized, which can pressurize this poison, and the poison can be transferred smoothly into the calandria. Okay. So now let us backtrack this from just a moment. Yeah. So now let us backtrack from this floating ball, and you can see like it is connected to some set of valves, and we will try to understand why these set of valves are required, and which is connected to a helium supply tank. And helium supply tank, basically it contains the helium, which is a gas, and basically it pressurizes. So whenever there is a demand to inject the poison into the calandria, these valves will be opened and it can pressurize this floating ball so that the poison can be injected into the calandria to terminate the fission reaction, to eat all the neutrons. Now let us see why these so many valves are required. Can you imagine if there could be only one valve instead of these 6 valves? And just like a tap, whenever I need a water, I can open the tap, and whenever I don't need a water, I can close the tap. So in this instrumentation also, I could have only one valve, and that could be normally closed during the normal operation of the reactor, and when it is required to be to inject the poison, I could open this valve. But what would be the problem with only one valve? Now suppose if the valve is stuck to open, there is some mechanical failure in the valve, and if it got stuck to open, then what would have happened? Definitely the helium pressure would not have passed to pressurize a floating ball, and my power would have risen up exponentially, and it may lead to the fuel failure, which can basically from which the radioactive can be released or can be exposed to the normal public, right? If some more barriers of the safety systems can be breached. To tackle with this scenario, it is advisable to put one more valve in the parallel, so that if one fail to open, at least the other can open, and the helium pressure can be passed from the other valve, and I could serve my purpose to shut down my reactor. But then why more number of valves are required? Now let us imagine the scenario after injection of the poison, and I want to after normalizing all the process parameters, after maintaining all the components, whatever the components has been malfunctioned, due to which the reactor regulating system was not working or the control system was not working. If I want to restart my reactor, then again I'll have to open up these to close these valves, 2 valves, which I have put in the parallel line. Now suppose In this scenario, the valves, any one valve is failed or is stuck to close. Earlier, I was dealing with valve failed to open. Here I am dealing with failed to close because I need to restart my reactor. Then what could happen? I would not be able to restart my reactor because one is failed to close. And again, the helium will keep on pressurizing this floating wall and in, the injection of the poison will continue. So to tackle with this scenario, let us put one more valve in series so that if one valve is failed to close, the other valve will be closed and it will ensure like that helium pressure is not passing through the poison tank. And hence we have to put one additional valve in series in both the parallel lines. So, okay, now it is well understood the configuration of these four valves or the necessity of these four valves. But what is the necessity of these two valves which are vertically arranged in each of the line? Now, suppose consider a scenario. There is a valve in the first. There is some leakage in the first valve, and because of this leakage, the helium pressure is passing, and it can malfunction the operation of the second valve, and it may happen like it can pressurize the floating valve. So what should happen? So I should be able to devise a mechanism so that I can release the pressure in that line between these two valves. So for that, to tackle this scenario, I have, put one additional valve that is known as vent valve to vent the pressure in between these two valves in both the lines, in both the parallel lines. And hence, these two valves should be opened all the time during normal operating condition of the reactor. And when there is a requirement to shut down my nuclear reactor, first I should close the vent valve. Then I should open all the quick opening valves or the fast acting valves. These are also known as fast acting valves, so that the helium pressure should not release through the vent valves and it can be released to the floating valve and it can inject into the calandria. And whenever I want to restart the reactor, I have to reverse the action. It means first I'll have to open the vent valves and then I have to close the quick opening. And you can see in this entire process, only these valves are dynamic in nature. Or otherwise, all the components are static in nature. And static in nature, the components which are static in nature, of which do not change the state, are more steady, are more robust, are more safe. Because there is no randomness, very rare probability of randomness in those systems. So it is advisable to model the dynamics of these valves. Okay, so I have created a Petri net model to capture the dynamics of these valves. Let us try to understand the model. So this is interestingly, you can see like because I have not assigned the weight of any arc. So the weight of the every arc is 1, is treated as 1. And the first, if you see the place PPD, it represents when there is a token in this place, it will represent like some trip parameter has deviated. It means there is a demand to shut down my nuclear reactor. Trip parameter means some process parameter had deviated from its normal range, and I need to shut down my reactor there is an emergency situation. and it is getting the data from some field sensors. And then the TTPD, it is a transition which basically represent that it is sending the signal to create the logic condition and to energize the relay to close the vent, because I need to close the vent valve. So it is triggering two basically actions. One, I have to create the logic condition. Logic condition means what valve should be open, what should be closed, and it is a kind of flag also. For example, if I'm going on a road and some construction work is taking place, I could find there is a flag, red color flag, where it is written that road construction is going on, so that I can so that I can take the alternate path. Okay, so it's a kind of flag basically. And when the road construction is done, then I can, remove that flag. So this is the logic condition. So this TTPD basically it sends the signal to create the logic condition, as well as it energizes the relay to close the vent. So let us see first logic condition creation path, that is horizontal. So there is a place PLC on. If there's a token in this place, it represents that logic condition has been created. And when it has been created once, I have to hold it up. So TTLCH represents that logic condition is on hold condition. It is a trigger basically to that it has to put on hold. And when there's a token on TLCH, it represents that logic condition is on hold. Now coming to the vertical line, which is basically representing the operation of the vent valves or the quick opening valves. So PREVV, if there is a token in this place, it represents that the relay has been energized to close the vent valves. And the TVVC, it represents the trigger to close the vent valves. So when the vent valve will be closed, the token will come into the PVVC. And after that, after closing the vent valve, I have to open the fast acting valve. So again, I have to trigger for opening the fast acting valve. So TFAVO, it basically triggers to open all the fast acting valve. So it will first see if fast acting valve is closed, which is an input to this transition, then only it will allow to open all the fast acting valves. Okay. Now, when here the injection will take place. And when I have done with the injection, and suppose I have turned off the logic condition as off, then my first action would be that I have to de-energize the relay to open all the vent valves, right? So PRDVV, it basically represents that the relay has been de-energized to open all the vent valves. And TVVO, it represents the trigger to open all the vent valves. And when the vent valves will be opened, it is represented by PVVO. And next, I'll have to close the fast acting valve so that I can put my reactor in operating mode. So after that, again, I have to trigger that fast acting valve close, and it will be reached, the token will be reached in fast acting valve PFABC. Now, one more interesting point that here I want to touch in the model. I have not touched two places. One is PFABCD and one is PFABOD. So these are just a redundant information of the fast acting valve open and close state, which is getting the information from the redundant field sensors, because we cannot rely only on one sensor. We have to have a redundant sensor and we have to compare both the values, and then we can come to the conclusion, and accordingly the action needs to be taken. Okay. So this in at the starting point, I have put the token on that fast acting valve is in closed state in the main information, main sensor information, as well as the redundant sensor information. So this is the entire. Now, after constructing this entire model, we have to go for the safety analysis. And for that, we have to draw the reachability graph. And we have already seen how to draw the reachability graph. We have to see the distribution of the tokens, and the tokens are distributed in only PPD, PFAVCD, and TFAVC. So because these tokens are only responsible to change the state of the system, so let us ignore rest of the places just to save the space. And we have written the first state is, we have mentioned all the places which is having this token, PPD, TFAVCD, TFAVC. Then if you look back into this figure, only one transition is in enabled state, that is TTPD. So once it fires, the token from PPD will be moved to PLC on and PREV. 1-1 token. Why 1-1 token? Because the weight of the output arc is 1. In these, so 1-1 token will be placed in these output places. So now, after TTPD, next is PPD has been transformed to PLC on and PREVB, and rest of the places will remain same. And in this way, we can keep on deducing till we reach or till we cover the entire state space of that particular system. And this is the entire reachability graph. Now, once I draw the reachability graph, I have to analyze each and every state, because every block is representing the state of the system, because it is representing the distribution of the tokens, and I have to analyze each and every state. So the idea is you identify all the system states and identify whether any state is in risky state or any state is in hazardous state, and try to devise some mechanism so that hazardous states can be avoided. So if you see, there are the two hazardous states. We will discuss how, which I have, denoted by a left upper solid circle, that is S3 and S6. So these two states are basically known as the hazardous states. Now, why it is these two states are hazardous? First, let us try to analyze the S3. We see like there is a PLCH, means logic condition is on hold. And if my logic condition is on hold, it means my fast acting valve should be open, because I need to inject the poison very fast. And if you are able to see here, both the redundant and main information, sensor information, represents that fast acting valve is still in closed condition. So it is a very risky state, and I really need to avoid this state. Now coming to the analysis of S6, here there is one controversial information. We can see like PFAVOD, which represents like fast acting valve is in open state from the redundant sensor, and PFAVC, it represents that fast acting valve is in closed state from the main sensor. It means both the information are controversial and to which sensor I rely. So this is also a hazardous state. And hence I'll have to deal with these states. Now let us see how we can, deal with this state. First, try to understand to address this as 3. If you see S3 is originating from S2 state. And if you go back to the S2, there are the 2 states which are originating from S2, that is S3 and S4. From the firing of the 2 different transitions, that is TLCH and TBVC. And hence one transition is leading to the risky state. One is reaching to the safe state. So why don't we do something so that when these 2 transitions are in race condition, parallel transitions are known as these transitions are in race condition. So I can prioritize one transition which is leading to the safe state. So I should prioritize TVVC so that whenever these 2 transitions will be ready to fire, always TVVC will fire and it will not fire. So never it will be a possibility that I can confront with S3 state. Now, how to do it, we will see later. But okay, this is the idea. We can do that. Now, similarly, if you look into the S6 state, we can see it is coming from the 2 states, that is S3 and S4. And we have already devised a remedial action to avoid the S3. So there will be no possibility to confront this S6 state from S3. It can only be possible to coming out from S4. And from S4, there it is leading to the 2 different states, that is S6 and S7. And again, the situation is like S3. So because this 2 transitions are in race condition, TLCH and TFABO. So let us prioritize TFABO so that this S6 can be ignored. And in this way, like I can get all the safe states also only. We can avoid the risky state. Now coming, let us coming to the point how we can do that. So first we have to, change our model, which we have made. So because I have to keep the low priority to the TLCH, and when 2 transitions are in race condition, and I want to keep one in higher priority, then keep one additional place or add one additional place in between these 2 transitions which are in race condition from the transition and connect that place from the transition whom you want to put on the high priority and to the transition whom you want to put on the lower priority, so that every time the lower priority will only be fired when it will see the token in the input place, and which is just the additional place that you have kept, and which is the output place of the transition whom you want to keep on the higher priority. So that the places the token can be deposited into this additional place only when the high priority transition will be fired. And hence I can serve my purpose. I can. So it's so here because there were the 2 cases where the 2 transitions are in race conditions. One is TFAVO and TLCH. So I have put one additional place here. Sorry, one is I1 and one is I2. I think 1 and I2 are missing. And I want to similarly lower down the priority of TLCH in the case of parallel transition with TVVC. And now, after that, let us try to draw the reachability graph. And when we draw the reachability graph considering this I1 and I2, we see there is no risky state. But here the story doesn't end at all. Because as an engineer, we have to optimize the process as well. And you can see these additional places are not serving any purpose for the functional requirement. It is only fulfilling the purpose of the safety. And hence, why don't we try that two cases? First, keep only one additional place, remove another additional place and try to draw the reachability graph. If I find I try to analyze then all the states. If I find any risky state and do vice versa, means keep another place and remove one place, additional place, and then draw and see if in any case are we getting the reachability graph where all the states are risk-free states. And if I'm not getting, then I don't have any solution. I don't have any alternative. I'll have to go with this model only, right? So because every additional, place will account for the computational complexity as well as the space complexity, and hence we have to go for the optimization. So we can try like putting only I1 state, and again we are able to see that there is a one risky state which is represented by this solid triangle in the left upper state. And if I consider only I2, I see that there is no risky states, only which I have shown the states with the solid circles. These are only the end states. So yes, at least I can optimize my process. So this is the modeling part. Now let us try to look about the implementation part, how we can implement it, like prioritizing of the transition and all. So we know like a real-time operating system, it provides a feature to the application software through which we can prioritize the task. So therefore, the other way to impose the precedence among the parallel transition is to avoid the risk state, to enforce the firing of the transitions as per the defined priority, right? So which can be done by enforcing the timing constraints into the design. So in case of our study, the following constraint, this constraint, that is minimum of TTLCH is greater than a maximum of TFAVO. It means every time I'm ensuring life, this TFAVO will be fired whenever there is a race condition in between these two transitions. And I can put this constraint so that it can be checked by the hardware or the software logic as per the requirement. If the system fails to meet this constraint, I should build a logic into the design that the control reaches back to the originating state before the risk state, so that it can retry the process and meeting the safe state. And this logic can be achieved by the soft watchdog or the hard watchdog. In case of the hardwired system or module, the hardwired logic must send a periodic pulse to the watchdog. The moment the constraint given in that equation fails, this equation fails, it must stop sending pulse to the watchdog. And the watchdog must maintain the current and its previous state. So once this watchdog stops getting periodic pulse, it loads all the dynamic variables which are of the previous states. And the other possibility is to reset a microprocessor IC through the reset pin, which can reset the system state. So the watchdog that we were discussing can be implemented as a software watchdog or the hardware watchdog. If it is implemented as a soft watchdog, then it is known as soft watchdog, otherwise hard watchdog. Similarly, in the case of software system or module, the software must send a periodic pulse to the watchdog to process in the same manner as the hardwired system. Uh, but again, we have to like evaluate because it is a safety critical system and we need to investigate my system from different angles. As I said, the first principle is I need to stretch my system. So suppose, let us consider a worst scenario that my logic condition is created to trip the reactor and the embedded system closes the vent valves to satisfy the interlock for the poison injection. But because of some security issues, because these are if your system is distributed in nature, some embedded system is there, from the field sensors are there, they are sending the signal to the embedded system. Embedded system is sending the signal to the display unit, and display unit is, sending the signal to actuate the field devices like this. So some bad signal suppose comes, which is overriding my closing logic, because closing activity is a very crucial activity. We'll have to close the vent wall. Or so how it can be identified? First, it can be identified by the consistent or the inconsistent information in VFAVO and its duplicate sensor, because the same attack in both the redundant line is very impossible, in next to impossible. So suppose it may be, as a system, it may be a real condition or a fault, I don't know. But for my robust design to tackle these kind of scenarios, I should build a logic into the design that in either case the system treat that fast acting valve is in closed state and resend the signal to open it immediately. And how I can do that? By introducing one more safe state in between, that is known as TSAFAV, so that it can ensure that if fast acting valve is in closed state, then it can pull the token from the fast acting valve closed state and intentionally or enforcing it to close is to open state. Right. So again, to remove the conflict, so there are the two parallel transitions, SFAV and TFAVO. So again, we can, to remove the conflict, we can put a constraint for the safety. Okay. And now the design can be validated by drawing the reachability graph. And this is the reachability graph. And where we can see like there is no risk-free state. Now all the risks have been taken care by our model, and we have seen the implementation, how we can implement it. So similarly, this analysis can be further investigated for more and more issues. So it may be a time-taking process and much effort may be required, but the benefits overweigh them, looking from the safety perspective. And hence, if your system is large in nature, then probably you can decompose your system and you can identify what are the very important functionalities that are very critical with respect to the safety. You can, and then you can do the analysis of those important functionalities or modules. So in the similar fashion, it can be done to more number of components, and then you can keep on integrating those components. And one, we should understand one thing, that all the risks do not have the equal probabilities. So we have to prioritize the risk depending, and there should be a proper balance between the effort that you are going to put in and your economical and your schedule of the particular system. So this is uh, these are the bibliography where some of the publications based on this has been published. You can go through all those publications. And so that's all I wanted to discuss. I'm so sorry I have to go little fast because of the lack of the time. So yeah, so in case of any questions, I'll be happy to answer.
Participants, you please ask the questions in the chat box. Sir, one question has came, sir.
Yeah. Can we use this safety system while need a fast control on the neutron production, even when control rods work properly or work slowly than our need? See, first of all, the control rods are the mechanical actuators. Here basically we were putting the poison, which is a fluid, and basically both are that is the shutdown one system. This is shutdown two system, and both are as a redundant system, And yes, this safety system basically it is used to control the neutrons very quickly because generally the entire action for injection of the poison needs to be done in few milliseconds, probably 16 to 20 milliseconds. And it has a proper analysis, like because the neutron population also grows exponentially and the power also rises exponentially. So it has a proper analysis, and based on that analysis, if it is able to take action within 40 milliseconds, so it is able to control the easily control the any mishappening into the reactor.
So, any other questions, participants? So, if no other questions, then we will call Petri. Yeah. So, yeah. So, thank you very much, sir, Lalit Singh sir, because we are sorry for the because this is the lunch time. I cannot predict which speaker will take more time. So,
Sometimes it happens, right? Yeah.
Yeah. So sorry for once more. Any other things participants can share in the because SAR is also having one more session tomorrow also the same time. And we, at that time he will able to discuss about the reliability analysis of the mechatronic systems. The participants can also discuss tomorrow. Also, they can able to discuss. Okay. So if there is no other further questions, so then we will call the session. And once again, we will meet at 3 o'clock for the hands-on session on the MEMS software. Okay. So thank you, Lalit sir. Once again, yeah, we will meet you tomorrow.
Thank you. Yeah.
Thank you. So participants, we will meet at sharply on at 3 p.m. once again for our hands-on session, and you get ready with your laptop or the computer, get ready with it, and we will have the simulation software get ready. Okay. So then I'm signing off. We can meet you at 3 3 p.m. Okay. Bye.